that's L over 2, times 100 times the sine of 140 degrees minus x times 50.
Wait, I thought the mass of the ladder was 10 kilograms.
It
Yeah.
is.
50 is for the person.
Then why are we doing 100 right there?
It's the weight.
Oh, what? Wait, I thought it would, isn't the weight 98 then?
Isn't the weight what?
Isn't the weight 98? Cause isn't it 9.8 times 10?
Earth 2.
Oh,
Acceleration due to gravity, 10 meters per second squared.
okay.
Let's make that more explicit, since it's come up a couple times here. Now, if you wish to put the problem on Earth 1, have at it. X times 50, actually, it's
Sine
times
130.
500.
Sine 130. 30.
No, 140.
But it's 180 minus.
No, we're on the second term. Second term is theta plus 90.
Right, 140.
I assume you were just testing me.
I was looking at the third.
Okay, now we're up to the third. So that's 15 times y2, which
Which was-
is 240, times the sine of 130 degrees. You're just ahead of your time. Equals 0. So now, like a jug, what are the chances that the first two people that have answers will have the same answer?
That would be funny.
The answer is 35.4.
I got 7.0806 meters.
7 point what?
0806, so 1. Yeah.
I was joking.
In that equation, did you, the negative is distributed to all the terms, correct?
No,
Well, the parts.
right, that is a term right there. That term is negative. Even, there's no addition within that term, so there's no distributing of it.
Yeah, I got the same thing as Helen. I forgot that we switched it from Earth 1 to Earth
You forgot that we switched it to Earth 2?
2. Yeah.
Yeah, that's gonna make that big of a difference. Sure, let's go with that.
Yeah, what?
How did you?
Yeah, I'm not convinced of that.
How did you determine X?
You actually, I suspect we'd get the same answer. Pardon?
How did you determine what X was?
What?
X was.
Well, we're solving.
We're finding that.
Oh,
That's because that's some number, the coefficient of x is some number, it's solving one equation, one unknown. All right, so we got two people at 7, but roughly 7.1. You got something different?
I was calculating each individual term,
Right?
and I have not calculated them all yet, but I'm definitely sure I'm wrong.
Okay.
So,
All right, I do want to point out one other thing here. So 7.8, there are units here.
I don't know what they are.
Meters.
Yes. It's how far up the ladder he's gone. So just before he gets to the halfway point, the ladder's going to slip. If we had gotten a negative answer, what would that mean?
you have to go down the ladder.
it would
Which
slip.
means, in terms of, we set the ladder up,
And then you start phasing through the floor.
yeah, it's going to slip automatically. He doesn't have to stand on it. If we got a number bigger than 15, which is the length of the ladder,
It won't slip.
at all, right? Okay. Now, when we were finding the angle, we basically had, let's just take this downward right here. weight doesn't matter, so 100 newtons. This angle is 50 degrees. R is this vector right here. We can go for that stunning visual effect. So there's R, there's F. What I really want to do is multiply perpendicular components. So what I could have done, instead of doing it the way we did it, where we did RF sine of theta plus 90 degrees, which is still legitimate, recognize also, if I just broke R up into its components, well, in other words, that component of R, that is just R cosine of 50 degrees. So I could have just done R cosine 50 degrees times 100. Because that's the same as cosine of 50 degrees. That is the same as the sine of 50 degrees. In the lab, I talked about the moment arm being the shortest distance between the axis of rotation and the vertical where the force is. What I'm asking for in the lab that you did is that length right there. So I wanted to make sure that I pointed that out. So for part D, where the meter stick was at an angle, for some nod, okay, got some nods of recognition. That's the number, for the moment arm, I'm looking for that number right there. And on that lovely, cheerful note, I think class is over.
Really?
Wait, what?
I think so too.
Yeah,
Guys, I think so
that's-
too. That's early.
We typically have breakfast, so.
Oh, that clock is wrong.
No,
No, it's not.
Yes, it is.
You
Well, I mean,
Sorry, guys.
as, I'm assuming you're all adults and that, you're not a prisoner here, so.
My phone says it's 9.
Ugh.
Don't mind if I do.
Yeah, so that's what I hopefully said. All right, never mind then.
Oh my god, guys, look, the speakers are JBL. So we're rich, so they can afford JBL speaker system, but they can't afford heating? Why is this building?
Sounds about right.
I'm just joking, guys.
Hey, school systems are
I'm
bipolar,
just
they're like
freezing all the time.
All right. It is just the clock is roughly correct now, right?
Yeah.
It's looking like 12 minutes.
Dude doesn't make sense. He's a freak.
All right,
On Master Chef?
any questions on this? I rushed through some of that at the end because I trusted the clock, but. All right, now the other rotational motion problem, we've dealt with static equilibrium, static rotational equilibrium. We obviously need to get into rotational lack of equilibrium. The classic pulley problem.
Oh my god, what am I doing wrong?
So mass 1 is equal to 70 kilograms, mass 2 equal to 50 kilograms, mass of the wheel is equal to 10 kilograms, radius of the wheel,
2.
thank you, 2 meters, 0.5.
2.5.
Just two.
No,
I heard 2 and then I heard 0.5.
Two.
Just 2.
Just 2.
2 plus 2.
Just 2, okay. And the question is, what will the acceleration be? Now, we've dealt with this before when we were dealing with an ideal pulley, but we're gonna remove one bit of idealness, is the fact that there is friction between the rope and the pulley. Matter of fact, the friction is so great that it is static friction between the rope and the pulley. So as the rope moves, the pulley will turn with it. There's no slipping going on here, so we're not getting rid of all the ideas. But we have sort of a perfect rotation of pulley. And once again, we start out with the force diagram. Except because we are now dealing with an additional force in between the two masses, because there's friction involved. The tension in the rope will differ from the left side to the right side. And I'm gonna give myself some more room here. What are the forces acting on this problem?
Weight
Of
of mass 1 and mass 2.
weight 1, weight 2,
Tension between the rope and the rope on the left and mass 1.
FT1, FT1, FT2, FT2. We are still assuming that the rope is massless, so I'm not worried about, not worried about these tensions being different.
Okay. There's no mass. Adding a weight.
If we have pulley.
And I think that's all.
Ultimately, that's sufficient. We do,
What about normal force?
there is a normal force acting on the pulley from the top, I'll call it Y sub R. Because the rope is hanging on it. It is exerting a normal force down. And there is something holding this up. I have 4 forces acting down, something's gotta be holding it up. So there is something holding it up, which presumably is a normal force. If I've got a pin holding it together and this thing is being pushed down, then there's a normal force acting up. I'll call it Y sub P.
But we already have Y sub pulley.
We already have Y sub pulley.
Yeah, W sub P. Why don't you?
I think that's an R.
That's an R there.
It'll be confusing for me if you do W sub P and that's for pulley, and Y sub P if you do if P.
Oh,
is
that's weight though, weight and normal force. Using the same subscript for the same object.
Can you use different subscripts, like screw or nail?
But it's all working on the pulley, so why would it not be the same subscript? That's the same thing of saying, can you make weight 1 and FT1 different, even though it's on the same mass? Or like the same object, if that makes sense.
That's the way I'm seeing it.
But they're two different objects?
No, the pulley has this normal force acting up on it and it has this weight acting down on it.
Okay.
Whatever, we're not gonna be using that, whichever we have. Because we do actually have, unlike the ladder problems and the static beam problems, we do have a natural axis of rotation. Now, if you really love doing math and torturing yourself, you may pick a different spot to be your axis of rotation. I would not recommend it. All right. We have some idea of which way this thing is going to go. Which way will mass 1 move?
That way.
I assume that was a point downwards? Okay.
Yeah.
So that's gonna move in that direction. This better be moving up. And the pulley, therefore, is gonna be moving that way. Equation solution?
J hat one,
Okay.
is FT1 negative FT1 plus weight one.
Now we're forgetting coordinate axis.
Well, we kinda know the coordinate axis because it's only like up and down, there's no left or right.
No, we probably
And
should want to
Excel-
define this, we're all on the same page.
Oh, yeah, we can do that too. It's right.
Well, for here, we'll make that positive. J1 hat, or we'll make that positive, J2 hat. And see, it's gonna run out to be positive, so K hat out. Equals
Equals mass times acceleration.
like that.
I
What's wrong with this?
don't know.
I feel like it should have a CP
Mass one.
or a sub P. A sub
Mass
C.
one. Mass one, yeah.
No, it wouldn't, because it's not twirling around itself.
Right,
No, she's right,
Mass
mass
one.
one.
that's one, yeah. Okay,
I didn't think it was like.
J2 hat equation.
T2 minus y weight 2 equals mass 2 acceleration.
It is the same magnitude of acceleration. And now for the pulley, yeah, we could do an I hat, or sorry, a J hat equation for the pulley. That really doesn't get us anywhere. What we really care about is the K hat equation. Or K sub P. Now, if we pick our natural axis of rotation, I have only two torques. I got the torque from FT1 and the torque from FT2. The weight, assuming that the pulley is designed normally, properly, the weight and the two normal forces are all acting right towards that center of mass, right at the axis of rotation, so they exert no torque at all. So we are left with, well, we have FT1 creating positive torque. So R FT1 minus R FT2 is equal to I of pulley alpha. The first two we're plugging in F equals ma. This one we're plugging in tau equals I alpha.
Tau.
Tau.
Oh, tau.
Okay.
Now the pulley, I need to give some, how is it designed? What is it? And let's just assume that it is a disc, a solid disc. If it is a solid disc, what is the moment of inertia?
It's
1/2 m squared. 1/2 m squared.
That's the one. So we have a substitution there. That's 1/2 mass of pulley, radius of pulley squared. We have formulas for these.
M1G and M2G.
Yep. And that'll take us to the next level. We do actually have to somehow connect alpha and A. So I have M1G minus FT1 equals M1A. I have FT2 minus M2G equals M2A. And then I have, well, I have only one radius, so I'll just simplify it as R FT1 minus R FT2 is equal to 1/2 MR squared, that's mass of pulley, MR squared alpha.
Right.
R sub P too, right?
Yeah, there's only one radius, so I was
Oh, okay.
going for the shortcut there, but yes, that is the radius of the pulley. Well, let's simplify that last equation if possible.
Okay.
Can we cancel out all the R's?
Not all of them, but,
Well,
because that's R squared.
squared.
But yeah, we can get rid of that R, and one of those R's. Now, what's the relationship between A and alpha?
Alpha is the angle and A is the,
Linear, okay. What's the relationship, if I have an object spinning, what's the relationship between speed and angular speed? Between V and omega?
I don't know. I thought I knew, but
Chapter 6.
isn't it like,
Abby, are you saying it?
yeah.
What's the relationship between the arc length and the angle? If I have a circle, if I have the arc length.
the arc? Well, okay.
The arc length and the angle, you said?
Yeah.
Oh, one
The
radius.
angle is directly proportional to the
One
arc
radian.
length is directly proportional to the angle.
Yep, and more specifically,
1 radian. Or radius.
if the arc length is equal to the radius, then the angle is 1 radian.
2 pi. 1 radian.
If we went for the entire circle.
Just
Standing
radius.
room only, the arc length is equal to
R theta.
R theta. Assuming we're dealing in radians. If I take the change in this divided by time, then I get V equals R omega. If I take the change in that with respect to time,
V divided by R